Now let us start with the next law, that is Lussac's law. This is pressure temperature relationship at constant volume. So at constant volume, we can write here the statement of the law. At constant volume, pressure of a fixed amount of gas. Pressure of fixed amount of gas is directly proportional to its absolute temperature. Capital T means P is directly proportional to T. Now remember here, in this case, the volume is kept constant. This is pressure temperature relationship at constant volume. In case of Charles' law, we have seen that this was temperature volume relationship where pressure was kept constant. In case of Lussac's law, at constant volume, pressure of a fixed amount of gas is directly proportional to its absolute temperature. Means P is proportional to T. We can write as P equals to K3T. We are taking here this as a constant. In case of Charles' law, we took it as K2, so we are writing here K3. If you rearrange this equation, you will get P by T equals to constant at constant volume and mass, small m, that is the mass of the gas. If you plot the graph for this particular law, so on x-axis, if you take temperature in Kelvin and pressure on y-axis, this way, goes on increasing in this direction. So you'll get such type of graph at different volumes at V1, V2, V3, and V4. It's at different volumes, V1, V2, V3, V4. And if you extrapolate this graph, it will reach to this 0 at origin, like this. And these are called as the isopores. Isopores means at constant volume. So what is this law? It says about at constant volume, pressure of a fixed amount of gas, it is directly proportional to its absolute temperature. So pressure, it is dependent on the absolute temperature. This is nothing but the Lussac's law. Because as the temperature increases, pressure also goes on increasing. The condition is that the volume should be kept constant. Now the next, that is Avogadro's law. We'll proceed further with the next law, that is the Avogadro's law. This is Avogadro's law. Avogadro's law. This law says that equal volume of all gases at the same temperature. Remember, the temperature is same temperature and pressure. Same temperature and pressure. It contains equal number of molecules. Equal number of molecules. I repeat, equal volume of all gases at same temperature and pressure. They contain equal number of molecules. It means that that is volume of gas depends upon amount of the gas, depends upon amount of the gas. In earlier laws, we were assuming that the mass is kept constant. So here amount of the gas is important, amount of gas. So Avogadro's he first time talked about the amount of the gas that we are considering. So amount of the gas is nothing but the number of molecules. You can interconvert those molecules into moles, weight into molecules, and so on. It means that this volume of the gas, it is proportional to N. N is nothing but the number of moles. So V will be equal to K4 into N. This is the constant, proportionality constant. Means that V divided by N equals to constant. We are just rearranging this. We put this N here below this. So it will be getting this equation V by N equals to constant at constant temperature and pressure. Temperature and pressure is being kept constant. Now this figure, that is 6.022 into 10 raised to 23. Here this is what we call as the Avogadro's number. And one more thing we should not forget, that is the 22.414, that is the molar volume at STP, means at standard temperature and pressure, 22.414 liters per mole. So what is this actually? I'll write here. Suppose we take 6.022 into 10 raised to 23 molecules of chlorine gas. Again, if you take 6.022 into 10 raised to 23 molecules of O2, oxygen. Again, 6.022 into 10 raised to 23 atoms of, remember here I am taking atoms, neon, or 6.022 into 10 raised to 23 molecules of methane. Now, if you put them in one sentence related to this figure, what we call as the molar volume at standard temperature and pressure. And write this way, like this, all this. So this is the volume of each gas, each one of them, whether it is a chlorine gas or it is a oxygen or neon atom or methane molecules or methane gas. So volume of each gas is 22.414 liters per mole. Liters per mole. This is what we call as the molar volume. This is called as the molar volume at STP, that is at standard temperature and pressure. Okay, means whether this is the number of molecules for chlorine gas, number of molecules for oxygen, number of atoms for neon, or number of molecules for methane, the volume of each one of them will be 22.414 liters per mole, and this is what we call as the molar volume at STP. Now, this number, we talked about this in basic concept of chemistry. This is Avogadro's number. This is 6.022 into 10 raised to 23. So this Avogadro's number is equal to the volume of gas, each gas is equal to 22.414 liters per mole. This is nothing but the molar volume at STP. Molar means here you have to consider the number of moles. Means you need to convert those molecules into moles, and then you will get the volume for that particular gas. Okay. So we'll be solving the numericals based on this also. We will proceed further. You just remember here. This is important point. Now further. Now this IUPAC, according to International Union for Pure and Applied Chemistry, which is known as IUPAC. According to this IUPAC conventions, which is standard pressure, it is 1 bar, which is nothing but 10⁵ Pascal. Okay. Standard temperature, it is 273.15 Kelvin, which is equal to 0 degrees Celsius. And molar volume of an ideal gas or mixture of 2 or more gases, it is equal to 22.71 liters per mole. Now, these are the values according to IUPAC, and old STP conditions were like this. Remember this old STP conditions. We used to use these values only. That is standard pressure this much, 1 bar, or temperature this much. But old STP conditions were like this. That is standard pressure, that is 1 atmosphere, which is nothing but 1.013 bar. These interconversions you should be aware about. Standard temperature, which is nothing but again the same, 273.15 Kelvin, which is equal to 0 degrees Celsius. And molar volume of ideal gas, which is equal to molar volume of ideal gas equal to 22.414 liters per mole. Okay. So this is about the Avogadro's law and the different values for the pressure and temperature and volume. So this information you will need while solving the numericals based on this lesson. Now we proceed further for the next one, that is the relation between molar mass and density of gas. Which is denoted by small d. So we know that small m, that is the number of moles, which is equal to small m divided by capital M. So what is this small m? That is the mass of a gas. Capital M, that is the molar mass of the gas. So this division will give you number of moles. Now we have this equation V equals to K4 into N, which is according to this Avogadro's law. Now, where this, we know that M by V, that is mass upon volume, it is nothing but the density, isn't it? So here you can write V is equal to K4 into small m divided by capital M. Okay. Now, here, as you know that mass upon volume equals to density. So you can write in terms of capital M, that is capital M will be equal to K4 into small m upon V. We just rearrange the equation. This small capital M we put here and V will come to this right hand side. So we are just rearranging this equation, this upper one, V equals to K4 into small m upon capital M. So we wrote this equation in terms of capital M, that is the molar mass. It is K4 into small m upon V. So this V comes here and this M will go here. Now, in terms of capital M, this mass upon volume, that is nothing but the density. So you can write here capital M equals to K4 into D. So instead of this M by V, small m by V, you can write D, that is the density. Or you can write M equals to M proportional to density. Okay, means molar mass of the gas, it is proportional to density. It means that. So this is the relation between molar mass and the density of the gas. Now, a gas which obeys Boyle's law. We'll see further for the next slide. A gas which obeys, right here, a gas which obeys Boyle's law, Charles' law, and Avogadro's law. Avogadro's law. It's an ideal gas. Yeah, ideal gas. So what is this Boyle's law? We'll write one by one. This V is inversely proportional to P. This is what? This is Boyle's law. Boyle's law. At constant, in case of Boyle's law, what is constant? Constant temperature and number of moles, that is small m. Then V is proportional to T. This is nothing but the Charles' law. Charles' law, where this pressure and number of moles, it is constant. It's constant. And the third one, that is Avogadro's law, that is V is proportional to N, that is volume is directly proportional to number of moles. This is nothing but Avogadro's law. We have just talked about this. Avogadro's law, and what is where this pressure and temperature are kept constant. Pressure and temperature is constant. So you remember all the three laws: Boyle's law, Charles' law, and Avogadro's law. And remember the things which are being kept constant. In case of Boyle's law, temperature and number of moles are constant. Here, pressure and number of moles are constant in case of Charles' law. Okay. And in case of Avogadro's law, pressure and temperature both are kept constant. In case of Boyle's law, temperature constant. In case of Charles' law, pressure is kept constant, and in case of Avogadro's law, pressure and temperature both are being kept constant. Now, on combining all these above three equations, you can write here. On combining all the three equations, you can write that is V is directly proportional to N into T divided by P. Because we wrote this everything in terms of volume. So we just wrote in this form. This is inversely proportional to, so this P should go to the denominator, and what should be up on the numerator? T and N. So T and N in the numerator, and P should go to the denominator. So V is directly proportional to N into T divided by P, or you can write V equals to R into N T divided by P. So what is this N R? This is the universal gas constant. R is where R is universal gas constant. universal gas constant. Now this equation, this one, V equals to R NT divided by T or P, this can be written as PV equals to nRT. This is nothing but ideal gas equation. This is what? This is ideal gas equation. Okay, so this ideal gas equation you will need this year and next year also. So in the next lecture, we'll talk about values of this R, which is a universal gas constant in different units. Thank you.